A small block of mass m is kept on a rough inclined surface of inclination theta fixed in a lift. The lift moves up with a uniform velocity v and the block does not slide on the incline. The work done by the force of friction on the block in time t will be. Solution for this question. Inside a lift, let us assume that this is a lift. Inclined plane is there inside the lift on which a body of mass m is placed. Now, this entire system, that is lift, is moving in the upward direction with a velocity v. Weight of the body is acting vertically downwards and normal reaction is acting normal to the inclined plane. This is v direction, velocity, and friction is acting in this direction. So if mg can be resolved into components with respect to normal reaction, so this is mg cos theta in the direction of normal reaction and perpendicular to normal reaction mg sin theta. In the diagram, f is equal to mg sin theta, f is equal to mg sin theta, and distance travelled in t seconds. Distance or displacement, distance in t seconds. So s bar is equal to v into t, velocity into time. Distance or displacement, s bar is equal to velocity into time. See here, this is theta and here also this is theta. So opposite angle theta, then angle between the frictional force and displacement, velocity and displacement are in the upward direction. So angle between displacement and frictional force is 90 minus theta. Now work done. So W is equal to F bar dot S bar, work done by a frictional force. This can be written as Fs cos theta, or you can take it as theta dash for convenient. This we can assume as theta dash. F is equal to mg sin theta. F is equal to mg sin theta and S is equal to V into T. V into T. Theta dash is equal to 90 minus theta. It is cos 90 minus theta. We know that cos 90 minus theta is equal to sin theta. So therefore, mg sin theta Vt into sin theta, or W can be written as mg Vt sin square theta.